So, good morning once again. I'm glad you made it. The weather out there is not looking too good today, but I hope that by Friday will be better, or at least let's hope that in the next Sunday. Yeah, so let's hope that this is the worst it can get, and then it will be just improving until the end of the semester. So let me remind you that we are in the middle of our discussion of diagrams. Last lecture was actually the first full lecture dedicated to a diagrammatic representation. We discussed basic concepts of the Fermion lines used to represent creation and annihilation operators. We talked about vertices representing many-body operators, the super vertices in a Goldstone representation. Okay. Then we essentially discussed how to represent a product of operators by drawing the corresponding diagrams along the axis, which we call the time axis, which in our case stretches from left to right. And then we discussed, of course, one of the most important components of the diagrammatic language, namely the contractions of external lines. We learned that by contracting lines or connecting them, we end up with internal lines. So that means that we have to pay attention to two types of lines in diagrams: the external Fermion lines and also the internal Fermion lines. We learned that internal lines are either holes or particles. External lines don't have to have the well-defined character prior to the calculation, but internal lines always will be holes or particles, and their character depends on the orientation. So for the lines that go from left to right, we have holes. For lines going from right to left, we have particles. Okay, and then when we sort of talked about it, the issue has emerged: how are we going to label internal lines? Of course, in our initial example where we just connected one x dagger with one x, or one x with one x dagger with fixed indices, we realized that the resulting internal line will be labeled by two indices representing the Kronecker delta. Okay? The question is, what happens if our indices are not necessarily fixed? As you know, in most, I guess in the vast majority of calculations, indices that are at various lines will be summed over, because that's what we do in many-body operators. We are summing over indices. So let's discuss this issue today. And as you know, in order to do this, sort of at the very end of the last lecture, I said that I'm going to be using a sketchy representation of diagrams with these blocks. Okay, so let me remind you what we're going to be doing or using. So when I write a block like this, and when I have a line sticking out, labeled with a P, what I mean by that is a diagram that among its various lines and elements has at least one creation operator, which I labeled here with a P. So when you really think about what is the algebraic expression corresponding to this picture, it's some numerical factor, which is certainly a function of index P and other indices, and there could be 1,000 other indices. We're not paying attention to what we're not writing. And then, it has a creation operator among the operators, but it can have more. So I'm going to surround this by these dots just to emphasize that we're just emphasizing one specific line. We're paying attention to one specific line, which we'll be trying to analyze. Of course, if P is fixed, well, that's all you have to write. If P is summed over, you will have a summation over P. So I'm going to put it in brackets because that is an option, okay, that we have here. And if I draw an analogous picture that looks like this, okay, we'll say line P now coming into the diagram, then this formula is a diagram where among the various lines there is an annihilation line P, and there may be lots of things inside the block which we're not going to analyze. So, and we're going to represent this by a numerical factor corresponding to the diagram, which, as you know by now, is a sign, a weight, and all these matrix elements that are in the diagram. We'll talk about it for a long time. And then we have an annihilation operator among the various operators. And once again, if I sum over P, I have to have a summation. If I don't, okay, I just have the product of G and and the operator and everything else that we're not writing. Okay, so let's now try to sort of analyze these various types of internal lines that emerge in situations where the indices the lines we are connecting are labeled by fixed or free summation indices. Okay. What I'll start with, just for us to get used to this, using these blocks, I'll start actually by redoing the original example where we're connecting two lines with fixed indices. Okay. So what do we have then? Okay. So I'll write it as fixed indices. Okay, as our first case. So what I have is I can have only two situations. One of them will be, a block on the left with line sticking out, another block on the right with line going in. Okay, I don't have to consider a case where both lines are sticking out because those will not be able to connect those. We already know them. Okay, so they have to have the same orientation. So let's do this. That's one case. Of course, there's a second case formally. If you want to be complete about this, there will be a second case which I will process. Okay, actually, let's take this. There will be a second case where we'll have, in the leftmost diagram we'll have P coming in, and in the rightmost diagram we'll have, say, Q leaving. Okay, we'll come back to this one when we are done with the first. Okay. So let's see what is this picture. So we have one operator expression here times another operator expression here. The question is, what's on the right hand side? Okay. So what I'll do, I'll start doing some little algebraic work around that picture. So on the left, what I see, according to our notation, is some numerical factor f for the diagram on the left. Okay. Then the diagram on the right brings another numerical factor, which according to our general notation must be called G, and Q is one of the indices in it. Okay? What else do we have? We're not summing over P and Q because we said that those are fixed indices. And then we are now on the right-hand side of Wick's theorem. When you are on the right-hand side of Wick's theorem, you have an operator in the normal product form. So the next thing you have to write is a normal product form. Okay? What's in it? Among the operators you have xp dagger from the left diagram and xq from the right diagram. Okay? And we are supposed to connect them. That's what we want to do. So I'm going to draw this dotted line here, emphasizing that I want to contract them. That is an algebraic representation of what we're going to get. So one lesson you're already learning is anything that you draw in the resulting diagrams, as we call them, on the right-hand side of Wick's theorem is in the normal product form. Diagrams on the left-hand side don't have to be in the normal product form, but whatever you produce on the right-hand side is in the normal product form, because that's what Wick's theorem requires. Okay, so little lesson already there. Let's process this expression algebraically. So, what do we have here? Maybe I need more space, so I was a little bit too quick on writing this one. I'll redraw it, don't worry about it. Okay, what we have there is then, we have to evaluate the contraction. Let me remind you that this contraction xp dagger xq is chi p times delta pq. Okay, so if I now use this information, we end up with, well, you take this contraction up. When you do this, you will introduce some sign. So you can see already that when we'll be proving Wick's theorem in diagrammatic form, the sign factor will have to somehow emerge from this process of unscrambling our normal product. So I'm going to end up with, plus or minus. I'm not going to pay attention now to the sign. It's going to be plus or minus the chi function, the delta pq, and then we have the product of the numerical factors, f with a p, g. I can write actually the same p because there is delta pq, so I don't have to call it a q anymore. And then what is left is the normal product of all the remaining operators we did not pay attention to or did not contract. Okay? So that's what it's going to be. So the question is, what is the picture for this situation? Well, okay, I'm going to now try to go back. The picture will be this. We are contracting, we have these two blocks. Okay, we are contracting these two lines, we're connecting them together. Okay? The result is a line that goes from left to right. Well, we expected that, but you can now see this is enforced by the chi function. It tells you it must be a whole, okay, because chi is 1 only for whole states. And we have to keep both indices. There was nothing in our calculation that allowed us to get rid of P and Q. That is, I still have to label my line with P and Q as we did in our initial example. And we know now that if you have these two indices, they represent the delta, because that's what algebra tells you. Okay? So this is one rule that has already emerged. We'll remember that. Okay? So now I can, I'm sorry, I'm moving this blackboard so much, but anyway, this one goes up, and I'm going to finish this here. Okay? All right. So, in the same way, I can analyze the second case. I guess you already know what's going to happen. Okay? This is a situation which is sort of the companion situation compared to the first one. We have now line P going into the left diagram, line Q leaving the right diagram. We are trying to connect them. Again, algebraically, the one on the left, according to our notation, has a numerical factor GP. The one on the right has a numerical factor FQ. Okay? As you notice, I always use F if the line is leaving. I always use G when the line is coming in. Okay? Then we have a normal product. Okay? We're trying to connect P and Q. So for the P, we have an annihilation operator because that's the line coming in. For the Q, we have a creation operator because that's the line that leaves it. We are supposed to contract them. Once again, the same set of tricks. Take the contraction out. Remember that this contraction is pi p delta pq. So I end up with plus or minus, depending on what happens to the permutation I need to apply to take this contraction out. We have plus or minus pi p delta pq, the product of the numerical factors g with a p and then f with a q. Actually, I don't have to call it a q anymore. I can call it a p because there's a delta. So I have g as a function of various indices including p, f as a function of various indices including p, and then we have the normal product of all the remaining operators which we are not paying attention to. So again, the diagrammatic representation for this must certainly be, I draw it here, a situation where these two blocks on the left and on the right are connected with a particle line, and the fact that it's particle is in the pi. Okay? But I still have to keep both indices because there was nothing in our procedure that eliminated them. So I have to put them here, and that means that I'll read this as delta pq. But you see, one thing that you're already learning is that, well, two things we already learned. Whatever we're going to obtain in the resulting diagrams corresponds to operators in the normal product form. That's lesson number one. Lesson number two is that we don't have to really use these step functions anymore, because the left-right orientation tells you whether it's a particle or a whole. Well, that's a nice advantage. You remember, before we had to sometimes worry about what is chi, what is pi, and all that. We don't have to worry about it because this is already guaranteed. Okay? As a matter of fact, you could redo these two cases. They really, if you really think what they boil down to, they boil down to a situation where the first case, since we end up with a whole, in the first case we end up with a whole, right? Well, that means that, if P and Q happen to be particles, you would not be able to do that work. Okay? So de facto, the first case corresponds to, I'll just sketch it. I'm not going to maybe recalculate because I hope that this will be really repeating what I'm doing, right? The first case there is a situation where you have a whole line leaving the left diagram and the whole line coming into it. Okay? Certainly you can connect them. And the result is a diagram that has two indices ij at the line. That's what the first case is, right? In order to process this, I would have to really repeat this exactly, replacing p by I, q by j. And I would not write the chi function anymore because chi of I is 1. Okay? But the lesson is that when you have two diagrams of this type, where we are trying to connect the whole lines I and j, you end up with and both are fixed, you end up with a diagram that has an internal line labeled by both indices, and you interpret these two indices as a delta ij. Okay? So let's remember that this is, maybe I'll use a different color. let's remember that the presence of these two indices means delta ij. Okay? And the bottom case here, you can see we have a situation where the result is the internal line that goes from right to left. So de facto we did connect two particle lines. If they were holes, you would not be able to do this simply. You would have to say, well, it's a zero, right? So we know that the bottom case really is reduces to a situation where we're trying to connect two particle lines, okay, fixed lines. We end up with a picture that has this form. We have an internal line labeled with A and B. Okay, I would obtain this result by replacing P by A, Q by B. Okay, just redoing the whole thing. I would not have to write pi because pi of A is 1. So really, in this situation, we again end up with an internal line labeled by A and B, and the presence of these two indices means read this as delta AB. That's how you read this. You know, you see a line like this, you say delta. Okay, for it. You know, we'll be doing this really soon. Okay, so those, you know, but this is of course what I did right now. I didn't really do anything new. I just, I guess, formalized what we did before for single operators. Now I'm doing this for general operators that may be quite complicated, you know, because there is a lot of stuff that can go into the box. All right, but let's now look at cases we haven't considered. Okay, so let's consider a situation where one of the two lines is fixed or labeled with a fixed index, and one of the lines is labeled with a free or summation index. So I'm going to call it, okay, maybe fixed plus free. Okay, sorry for this shortcut, but that's what it means, right? One of the two lines is a fixed index. One of the other line that we're going to be connecting or contracting is a summation. Free in our language will mean here summation. Well, if you think logically about what's going to happen here, we'll have to consider 4 different situations. Okay? There will be a situation where the free line is in the left diagram, either leaving it or coming into it. So let's do the proper planning. Hopefully I process this. Okay? And there will be 2 situations where the right diagram has a summation index. So for the first one, if this one is summed over, so we're going to have a summation over P, okay? And the right diagram will be, say, you know, we know that it has, you know, this line eventually will become a whole line, so I'm going to simply assume that my right, operator on the right has a fixed line I, okay? I is fixed, all right? And, you know, the question will be, what's on the right-hand side? That's going to be our sort of purpose. Okay, all right, we'll do it in a moment. Let me say what is the other case here. The other case here will be, okay, now we end up with a line going from right to left, so we expect that the line that we're trying to connect here must be a particle. I'm going to call it an A, okay, just like we call particles. Of course, you know, you can say, why don't I call it a Q or something like this? Well, I don't have to, you know, if the line is fixed, so the word fixed means that you know what it is. If fixed means that I equals 3. Well, you just look at the list of your orbitals, you know, oh, 3 is occupied. Okay, so, you know, I really know. You know, unlike the P, Q symbols, which when you sum over, we use sum over everything. So, you know, you can't tell, right? So that's why you have to still use P and Q. But if you have a fixed line, well, you must know its character. It cannot be both at the same time. Okay? So those are the 2 possibilities. And of course, here we're also summing over P. And there will be 2 more where the operator of this type is here. On this stage. But let's process those 2 first, and then, we'll come back to the other possibility. So, okay, again, the question is what's on the right-hand side, so let's do a little bit of an algebraic work, just like we did before. So what do I have? I have a summation over P, okay, I have a factor, numerical factor F, that contains all these matrix elements and scalars and weights and so on, for the left diagram. It's a function of, in particular, index P. Then we have a G factor, numerical factor for the diagram on the right, which is a function of I among its indices. And then we're attempting, so now I'm going to maybe sketch a dotted line here, I'm attempting to connect these 2 lines. So what I'm doing really is forming a normal product in the right-hand side of which theorem, where we have XP dagger contracted with an xi. But what is this contraction? Well, this contraction is delta, as you know, it is delta pi times the chi function of p or I. You know, there's delta, so you know. So you can see what happens is that I don't have to actually worry about chi anymore because I chose this line to be whole, so the chi will disappear. Okay, then you have to just process this expression. You can see that delta will eliminate the summation. Okay, so there won't be any summation anymore. You will have plus or minus because, you know, when you take this contraction out, there may be some sign emerging out of it. So plus or minus, there's going to be an f factor where p is replaced by I, and the g factor, numerical factor, with an I that it had. And then, of course, times the normal product of all the remaining operators that you might still have. Okay? Well, you see there's a difference here between this and the previous case. Because right now, what I have is only I symbol here. So when I think about what is the diagram that corresponds to this, I'm going to draw it. We're going to have these two blocks. We know that they will be connected with the internal line emerging from our contraction. And the index that I have to put in it is not two. First of all, I don't put two indices anymore because there's only one here and here. So I'm going to label this line with a single index, and you can see there is a rule already. That index is an index of the fixed line. Okay? And if you now go back to our algebraic manipulations, that's exactly what we were doing. You know, remember when we were doing this algebraically, when we had summations, then canonical deltas coming from contractions were eliminating some summations. And that's what happened here. The summation that we had on the left-hand side is gone. All right? And the line that comes out must be labeled, that's a rule, must be labeled by a fixed, by the index that is fixed in this operator. Okay? So you can imagine that in the same way, I'll go to this case, in a similar...
You have to know in the box that P has been chosen.
Yes, yes, yeah, because that line goes into the box, exactly, that's an important point. Yeah, so remember, once there is a rest of the diagram, that line goes into it. So whatever the line arrives at some vertex. So when you read that vertex, you cannot use P anymore. It will be I now. Okay, that's how this works. And of course, I'll show you examples. You'll see lots of examples, that illustrate this so that we really get fully convinced that that's indeed the case. But I guess, right now I'm doing this at the sort of general level. Okay, so what happens here? Well, we already know what's going to happen, I guess, so I'm going to do it quicker. We have the G factor on the left, we have the F factor on the right, okay? We are trying to contract among various operators. We have XP and XA dagger. Contract them. We know when we read this contraction is simply delta PA times the pi function, pi of P or pi of A. Okay, so when I process this expression, we end up with, again, the summation over P will be gone. We'll have the G factor. We'll have, first of all, plus or minus, because of course, the processing the normal product will lead to this. And then we'll have a G factor with P replaced by A. The F factor had A in it already, so I just have to repeat it. And then there will be a normal product of the remaining operators if there are any. Okay? So the consequence of this is that the resulting diagram on the right-hand side is a diagram which is in the normal product expression, okay, with an internal line going from right to left, labeled with an A, because that's what you see here and here. Okay? As Ron already said, that's what's going to happen, of course. What's going to happen is that A goes into these diagrams, and wherever it ends, that you have to make sure that you read it as A everywhere, not just outside these blocks. I guess we've got my little shade. Okay, so you can imagine, I guess, that if I repeated these considerations for the remaining cases, I'll end up with a similar rule. I hope that it's now clear. So, the next two cases would be, okay, let's have now, say, line I on the left, in the left diagram, and let's have, say, line P coming into the right block, summing over P, okay? Do I need to redo the whole calculation, or can I just state what's going to happen? You can see what's going to happen. When you contract them, you will have, again, these two numerical factors. It's going to be f for this, g for that, okay? So, the result will be a diagram which will have an internal line labeled with an I, okay? Only. And this will be really a manifestation of a calculation where we do a summation, and you have f, a function of I, g, a function of p, okay, and then a normal product of various operators including xi dagger and xp, okay, and this normal product will lead to the chi I delta ip, so the summation over p will be gone, and we end up with plus or minus f of I, g of I times the normal product of everything else, that is all the operators we did not contract. And the final fourth case is, I guess I'll do it somewhere here. The fourth case is the case where the operator on the left carries a line with which is a particle line. The line here, the operator on the right carries an external line P, which we are summing over, so there's a summation. Okay, and when we try to contract them, we already know that we end up with a resulting diagram, okay, which will have this overall shape. Okay, we'll have these two diagrams. The diagrams on the left connected with an internal line labeled with an A, which is again the manifestation of a calculation where we have sum over f. You have g as a function of A, f as a function of p, and then a normal product of xa, xp dagger contracted. This contraction is pi a chi a p. Sorry, am I writing? Delta ap. Okay, which means that we end up with plus or minus g as a function of a. That's a numerical factor originating from the left part of the left diagram. F, which is where p is now replaced by a. That a is fixed. Okay, that's the part that originates from the right diagram on the left-hand side, and then we end up with a normal product of all the remaining operators if there are any. Okay, so you can see that the overall rule. Yes, I did something.
No. I have a question.
Yes.
Cases 1 to 3 and cases 2 and 4 give the same result, even though the order of the operators is different. So why is it that here they seem to commute, whereas in
No, they don't commute. They don't commute. You see, because what you have, you have. Well, they don't commute. The rest of the difference is in the normal product. Okay, so the operators in it will still follow the order. Operators from here first, operators from here next. Okay, I'm not writing, what you only see are these pieces that originate from our contraction, but you don't see, of course, all the remaining pieces.
Okay.
But of course, you're also right in the sense that once you have a normal product, you can rearrange operators if you please. That will cost you a sign. Okay, but in a way, we can sort of. The word commute is not the right word probably for it, but we can interchange them inside the normal product.
Just because we're using the black boxes here too.
That's right, because we're not showing everything that is there. That's right. So, yes, exactly. But that point, it is an important point, because we will be able actually to manipulate operators inside a normal product. So it's not, quite heavily actually, so that's useful. Anyway, the lesson in all of this is that when you connect external lines which are both free, where one is free, one is fixed, you end up with a resulting diagram where the internal line emerging from a contraction is labeled by a single fixed index that you don't sum over. It's just a fixed index of the operator on the left-hand side. Okay? All right. So I guess let's finish this discussion by processing the final case, which is, well, what happens when both operators have summation indices. And that is actually rather the most frequent case. I wouldn't say all cases, but in some statistical measures, probably most situations look like that. So we will have two diagrams. So I'm going to call it free, okay, in this sort of shorthand notation, free plus free. So I'm going to be attempting to contract external lines which are both summed over, okay? So there will be a situation like this, where this is P, this is Q, so P comes in, leaves the diagram, Q comes into it, or, maybe I'll do it here, okay, where a situation where the left diagram has the annihilation line P, the right diagram has the creation line, say Q, and we will try to contract them, okay? Both are summed over, so I'm going to stick here a summation over P and Q in front, okay? Because that's what we're doing. And let's see what comes out on the right-hand side. Once again, following a similar analysis. So what do we have on the left? We have a numerical factor F from the left diagram. We have a numerical factor G, which has Q among its indices from the right diagram. But that's not everything. We also have a normal product of various operators, including XP, dagger, and XQ, contracted. And we are supposed to sum this over PQ. So, we have to do a lot of things now. Okay? Well, let's see what is the algebraic result for this. Well, you have to compute this contraction. Okay? Well, this contraction, as you remember, is simply this contraction here. Okay, is chi p delta pq. Okay? So, let's see what does this mean. Well, so first of all, when I take this out, there's going to be a sign, possibly a sign change. So I'm going to write plus or minus. I don't know right now. Okay? Well, then there will be a delta. So we know what happens next. I'm going to replace Q here by P. I don't have to sum over both indices because I have a delta. So I'm going to be summing and say, oh, well, let's agree that I'm going to be summing over P. But I'm not done yet. Okay? I'm not going to be summing over P because in reality, there's also a chi function. Chi says sum over occupied states only. So before I rush, I should say, no, I'm not going to be summing over P. I'm going to be summing over I. I'm going to be summing over occupied states only, which we call in this course I, okay, or J or something. So I'm going to be summing over I, okay, and I'm going to have F where P is replaced by I, G where Q is replaced by I, that is the consequence of having delta PQ, and there will be, of course, a normal product of everything else in the expression, of all the other operators in the expression that we have, okay? So you can see that if I think about what is the proper picture for it, okay? So I'm going to now start processing, okay? I'm contracting these two, and it's going to be a situation where these two block diagrams are connected with a line which is actually a whole line. That's what chi function did for us, okay? Only one index because you have I here and I here, not two indices, but only one. But you have to sum this over. So right now what I'm going to do as a reminder, I'll say I'm going to be sum this over. Later we'll learn how not to write these summations in front of the diagrams. Okay, right now it's more algebraic. Okay? Well, what happens in this case? It's a similar analysis. If I connect them, I'm going to have a summation over PQ. I will have, let's have a little bit. I have a G, numerical factor G, and then numerical factor F for the left and right diagrams respectively. And then we have a normal product of X, P is coming in, so it's XP. Q is leaving, so that's XQ dagger. Of course, there are lots of dots around, so please make sure that you have them. And then we are contracting. Once again, this contraction is, we have to read it, it's going to be pi P delta PQ. So two things will happen at the same time. Delta will force Q to be P, and the summation will shrink to a single summation. But furthermore, there's a pi function which says sum over unoccupied states. Okay? So what my final result should be is plus or minus a summation over unoccupied states. Let's call them A, as we often do. Okay, and then there's a G factor where P is replaced by A, the F factor where Q is replaced by A, and then a normal product of the remaining operators in the expression. So the proper diagrammatic representation of it is these two blocks. Squeeze this, connect it together with the internal line which goes from right to left. We label it with a single index A, but now this index is sum over. Okay? Sum over A. I hope you can see it. Sum over A of this type of a situation. So you can see we're learning that in cases where both lines are free, that is, indices are summed over, we end up with internal lines labeled with a single summation index. And you don't have, you see, now this is a beautiful thing about diagrams. You don't have to worry about chi or pi function anymore. Because you know that if your resulting line goes from left to right, well, you're going to stick the whole index at it. If it goes from right to left, you're going to stick the particle index at it. Okay? So, you know, this is a nice thing about diagrams that, you know, certain things begin to slowly disappear. Okay? Alright, so, you know, we are at the stage where we have learned quite a bit. And right now, I want to maybe touch one more issue before. Well, maybe I should. Let's have, I don't know, do you want to have a little break now? Or? Okay, so let's have a little break, a few minutes, and then we'll do one more thing, and then we'll sort of try to summarize the rules, and then we'll start doing examples. Okay? Because I don't want to keep you forever waiting for all the precise rules I have to derive. We'll sort of try to do this by, you know, switching between theory, examples, and in this way we'll be appreciating what else needs to be done, okay, to finally come up with a rigorous, precise formulation, right? Once we know all of this, then we'll prove it. Okay. Any questions? Okay, good. Good. I learned that I asked them sometime they added you to the Blackboard.
Oh.
I don't know if Blackboard informs you about that
No.
incident or.
No.
Okay, but anyway,
good. It's good. Thank you for doing
yeah. So you know, so if you log in there, I hope that you can see all of these things of this. Because I'll be happy to, you know, print these things for you. Yeah. Just tell me what you like. We'll do it.
Yeah.
I guess I'll start cleaning slowly. We should have a bucket of water. Mop.
Doesn't,
or whatever they use.
yeah, it doesn't dry that quickly, is the problem.
So I was in elementary school, they used to do this, then they, at some point they stopped, invented better blackboards, but those are, you know, blackboards, you know, I'm old to remember blackboards which were not as cool as those. So then you would have a wet, they wouldn't have an accurate weapon, that would be a joke, but probably dangerous in school either. But you know, they would have a wet sort of sponge or something. In case you needed some help, you would do that. Okay, so I guess I'll maybe slowly continue going on. Okay, so we're at the point where we need to perhaps discuss one more item before I sort of summarize the rules that we've learned so far, because we've already learned quite a few rules. Okay, that is, you know, let's talk about the final sort of issue, which is the idea of the resulting versus admissible diagrams. So we already know that if I have a formula, a product of operators, say Ka, Kb through Kz, or the product of the corresponding diagrams representing these operators, then we already know that through contractions or Week's theorem will end up with a summation over resulting diagrams. That's how we're going to call them. Okay? Resulting diagrams. I think in Professor Joe Paulus's notes, I mean, they are sometimes called R diagrams. You know, okay, we could call it an R diagram or a resulting diagram. Now, we will actually learn that you don't have to draw all resulting diagrams, because, you know, all you will have to do is to draw non-equivalent resulting diagrams, because diagrams will recognize the repetitions in Week's theorem. So if, you know, some contractions repeat themselves, you'll just draw one diagram representing the entire group, okay, and then we'll have a way to identify the corresponding numerical factors. But there is one issue that I'd like to emphasize, is that you don't always have to draw all non-equivalent diagrams. Because in many situations, you always have to think about what I'm going to do next in my calculation. All right? You know, usually these operator products are in some context. So, and that context may say, I don't need to draw all diagrams. Maybe I just need to draw a subset which is relevant to the context. And we already know from our rules that one of the situations that is worth emphasizing is, well, what if I know right from the get-go that I'm interested in forming an expectation value of the product of operators, some many-body operators, as complex as you like, in the Fermi vacuum state. Then you know very well that if I try to use the equation, you know, here, okay, you would really have to, let's write it symbolically this way, you will have to compute expectation values of these resulting operators. Okay? But we know that expectation value is non-zero only when you have no uncontracted operators left. Well, in our language of diagrams, fully contracted means no external lines. So you know very well that in drawing your diagrams, all you need to draw are non-equivalent resulting diagrams with no external lines. You know, if you think about it, that's a lot less than if you wanted to consider all of them, because, you know, you have to close all the lines. So that's a small subset of all the diagrams that you can think of typically. Okay? So that's a, you know, please remember this, because we're going to be using this information. Well, as you know, the other popular situation is when you apply a product of operators on the Fermi vacuum state. And again, you could do it in two different ways. You could first process the product, end up with a summation of our resulting diagrams, and then apply it to the phi. But, well, we know that from our rules that if you have a situation of operate, the terms in the right-hand side of Week's theorem, which are all in the normal product form, then you have to restrict this case to a situation where all operators y are fully contracted. You remember we talked about, there was rule 97, right, which said that all annihilation operators y are fully contracted. Well, is there a consequence of this statement on our diagrammatic rules? Well, there is one. Because you remember, what are the y operators, diagrammatically? They are operators where lines are extending to the left. That's the y operator. In other words, once you process your contractions, you have to turn all external lines to the left. Okay? Because you're not supposed to keep any uncontracted y operator. Okay? So we have to have, sorry, this is y diagram. Yeah, so we have to do this, right? Because, annihilator y is, this is y. Okay? I said it wrong there. So this is y. So you're not supposed to end up with diagrams that have lines, external lines extending to the right, because those will be uncontracted y operators. Okay? So in other words, I'll cross it. This cannot happen. All your external lines have to be extending to the left. This should be obvious. I could just say, okay, I'm done with explaining this. But I'll explain it one more time so that we get used to sort of how diagrams do that. How diagrams force you to sort of force all the lines to start moving, say, in one direction. Okay? So, let's do a little analysis, right? So what is KR acting on the phi? Well, in our sort of language, it's two things can happen. You can have a diagram R, that's how I'm going to call it now, okay? Where say one of, I'm going to again emphasize one of the lines, where we have one of the lines is, say, a creation operator line, and you have to sum it over various indices, including the P, acting with this on the phi. The other case will be where line P is coming in. Okay? So let's process this case, and let's see how diagrams force you to somehow turn this line to the left. Okay? It's not a bad exercise to go through, so let's do it. So, if you have a picture like this, we already know how to interpret these block diagrams. We have a summation over P. For a diagram like this, we have a factor F, which corresponds to all the matrix elements and numerical factors in the diagram. And then, since we are now on the right-hand side, this is the resulting diagram. That means that we have a normal product on the right-hand side. And in that normal product, there is an XP dagger operator. That's what this picture represents now. And all of this acting on the phi. This is an algebraic read of the picture. Right? Now, if you have a summation like this, you can split that summation into two pieces. A summation over the occupied states and a summation over unoccupied states. Okay? So I'm going to write it. Summation over I, and then I have a factor F where P is replaced by I. Normal product of various operators in our block. One of them is xi dagger, acting on the phi. And the second contribution will be a summation where you pick up the unoccupied states in it. Okay? So we have an F factor where P now is replaced by A, normal product where XP dagger is replaced by XA dagger acting on the phi. Okay? Those are the two sort of contributions. And let's analyze them. Well, in this contribution, we have xi dagger. Xi dagger, when you translate, is yi. Xa dagger, when you translate, is ya dagger. Okay? Well, what's going to happen to this operator inside the normal product? When you have yi, okay, then yi will have to be moved to the rightmost position. Okay, that's what we do in normal ordering. When you do this, you end up with a situation where yi acts on the phi. But yi acting on the phi is 0. So this summation does not contribute. Okay, I'm going to cross it out then. Maybe we'll put blue. Okay. there is no reason for me to cross the other part, because YA dagger can safely act on the phi. Okay? So we're just left with the second term. But what is the meaning of the second term? Well, let's read it back. Let's try to get our block diagram. So what you have is a block diagram, and we have to do two things at the same time. We have to have a creation operator, which is the line leaving the diagram. At the same time, it must be a particle line, which is oriented from right to left. The only way for me to reconcile with these two requirements is to turn our original line this direction. Okay? It has to be stretched to the left. Okay? Of course, we're not going to be bending them. Actually, you're going to nicely write them this way. Okay? Right now, I just want to emphasize the word that, it was sort of leaving from here, so I want to sort of say, okay, it still leaves from here, right? But it has to turn in this direction. Okay? And I will write that phi, because of course you can imagine I could also have a diagram where there's no phi, for some other reasons. It could be just an operator. So, sometimes we have to remind ourselves, sometimes we don't have to write it, because we know that everything acts on the phi, so then there's no point in writing it. But, here I'm going to do this just as a reminder. But anyway, line has to turn left, because, that's what this manipulation produces. Of course, we knew it, as I said. We have to stretch this line to the left. Sum, yes, right. Sum over A, perfect. Yeah, thank you. Okay, so that's what's going to happen. Of course, we could of course have a situation where A is fixed, P is fixed, right? But of course that means that if P was chosen to be occupied, then you wouldn't get anywhere with this, right? So you'll be able to claim, oh, that diagram has a wrong line in it. I mean, the one that doesn't lead to anything non-zero. So, what is the second situation? Well, the second situation, as you can imagine, okay, so I guess I can say or. The second situation would be, we have say, summation over some indices. We have a block, let's call it R, where line P is coming into it. And then again, we can analyze it. So we end up with a summation over P. We have a G factor, it's a function of P, and then a normal product of X that includes XP acting on the phi. It's XP now because this line is coming into it. Okay? And once again, I have to split the summation into two components. The first component of the summation, so if you could still see at least the bottom part of the top, or more if you like. And then we end up here with a summation over I. We have a G factor, which contains I. We have a normal product. We have Xi in it. And then the second component will be a summation where we sum over A. And then we have G, where P is replaced by an A. And then we have a normal product where we have XA acting on the phi. And as you can see, again, we have to, as you can see, one of the two terms will drop out, because after translating this, this XI here is YI dagger. This XA here is YA. Now, in the normal ordering, YA has to be moved to the right position. Okay, so you have to move it right here. We know that YA acting on the phi is 0, which means that the second term drops out, and you're left only with the first term. And now you're supposed to draw a picture that represents it. It's going to be our diagram R, where line that we have in it is the line that comes into it, that's Xi, and it's a whole line. To reconcile with these two requirements, you have to turn your line in this direction and orient it this way, okay? And sum over I, okay? And of course act with it on the phi to read the final result. But you can see no matter what I do, the diagrammatics or the algebra that we're using forces us to stretch these lines, extend them to the left. That's the diagrammatic manifestation of a statement that all annihilation operators Y are fully contracted. Only Y daggers are left. Okay? Alright, so I guess we're at the point where I can sort of summarize all the rules that we know, and then we'll start processing examples. Okay, with the rules we know by now. Those are not all the rules yet, but at least we already have a big chunk. So I think it's worth exercising. Okay. So in summary, let me sort of summarize the key steps of a diagrammatic calculation. Any diagrammatic calculation. You see, that's the thing I want to also emphasize. In this course, you're not going to be learning diagrams only for MVPT, or diagrams only for some other theory that I like or not. Okay? We'll talk about diagrams for any calculation. Right? So what we've learned so far is that in a diagrammatic language, the basic steps are as follows. The first thing that you have to do, say point 1, is to represent all operators on the left-hand side, and in our case this is, you know, KA, that's how I call them, through KZ, okay, by the corresponding super vertices, right, if we use this language. Right now super vertices, and later we'll use also Huguenot's vertices. Right now we're talking about Goldstone type. It's okay. Right? So you know we're in a situation where you have a product of operators. We're supposed to draw them along the time axis. Okay? And using our diagrammatic representation. That's an obvious step. Well, then we proceed to the right-hand side. That's going to be the second step. Maybe I'll emphasize along the time axis here. Just to remember that that's what we do. And the time axis in our case goes from left to right. Okay, second step is we'll be forming resulting diagrams, right? So the second step might, you know, if I want to write it rather shortly, then it will be form all admissible. Okay, that's one word. Admissible by the context you are in, like an expectation value, if that's what you're doing, or acting on the fee. So form all admissible, non-equivalent. That is still a little bit of a mystery, we need to discuss this. Resulting diagrams. That's the right-hand side, so I'll write it here. Sum over R. Call them KR, okay, by contracting external Fermion lines of operators on the left-hand side. So I'll just say briefly, by contracting external Fermion lines of KA through KZ, okay? So that's what you do next. Once you're done with this step, you have a bunch of diagrams on your piece of paper, for example, where you work on it, or on the blackboard. Okay? Then you read the diagrams, of course, right? So then, of course, you know, the situation is straightforward. Just evaluate each resulting diagram. KR, right? And we know that in this evaluation, I already gave you a hint what's going to happen. There's going to be, you know, maybe I'll actually emphasize this. It's not bad for us to keep seeing this formula multiple times. Each KR will be a sign, a weight, a summation over possibly internal and external indices, internal from contractions, external from uncontracted operators. There will be some scalar factor, dr, labeled by internal and external lines, and there may be an operator part labeled by the external lines. You remember I wrote that formula before, maybe to emphasize the meaning of it one more time, just briefly. We expect that every diagram will be read in this way. The sign, we have to learn how to do it. The weight, we have to learn how to do it. We'll label all the lines with the internal indices of internal lines, indices of external lines. We'll have scalar factors. And we'll have an operator part. If operator parts only, if you leave some uncontracted lines, you know, in an expectation value, you would not see an operator part. There is none, because you contract everything, right? But in some applications like this one, you will have external lines. So operator part. Okay, that's how we'll be reading them. That's the evaluation process we have to learn. Okay, what else have we learned to summarize these little pointers? Maybe point, I don't know, A through C. Okay, so A. We learned that in forming internal lines, we use certain rules when it comes to their labeling. So, internal lines are labeled by, and there will be 3 subcases, we label them by a single summation index if the corresponding external lines carry free labels. Okay? So if you are connecting 2 external lines that are free, then you end up with a summation line, and we know that that summation line will be a whole or a particle depending on the left-right orientation. Okay? The other possibility is that, you know, we have to label the internal, okay, the internal line, internal lines have to be labeled by fixed labels. So we can write here that we label in an internal line by a fixed label if one of the corresponding external lines prior to contraction carries a fixed label. Okay, so that's the second rule that emerges. One of those other statements. And the third possibility is the situation where we have to label an internal line with 2 indices. So we'll say that an internal lines can be labeled by 2 fixed indices, okay, which correspond to Kronecker delta. So maybe I'll say this here, giving Kronecker delta. If the corresponding I probably have to go below with this, so let me continue here. Hopefully, if the corresponding external, maybe slightly higher, external lines prior to contraction carry fixed labels. Okay? So those, you know, so in addition to rules 1, 2, 3, we have these additional pointers. Maybe I'll just go down slowly. Nico, can we see, because, you know, right now I'm having a little difficulty here with the spacing, and so hopefully you can see this. Okay, so we have a rule that once you start forming internal lines, you have 3 choices to make. You can label them, you will label them with a single summation index if the corresponding external lines carry free labels. You will label internal lines by fixed labels if the corresponding external lines prior to contraction carry a fixed label. And the third possibility is this one here. Stretch across these two blackboards. And we'll use two fixed indices if the corresponding external lines have fixed indices. And then you read this as a delta. Okay? Another thing worth remembering, maybe I do it here, is, let's call it point B. So we have, okay, in labeling internal lines, you have to remember that they are either holes or particles, right? So internal lines are labeled by hole or particle indices depending on the left-right orientation. Of these lines. Okay, so when you start forming internal lines in the resulting diagrams, you have to look at the arrow, where it goes. If it goes from right to left, it's a particle. From left to right, it's a hole. Okay? But of course, rule B has to be combined with rule A. Because that means that, you know, it could be a free, that is summation hole index, or summation particle index, right? Or fixed particle or hole index, and so on. And finally, it's worth emphasizing that the external lines of the resulting diagrams that remain uncontracted keep their original free or fixed labels. Okay? So external lines essentially propagate into the right-hand side. Okay? The only difference is that the external lines will be read inside the normal product. Because we know that, right? That the right-hand side is always normal product. But, you know, if you started with a summation line on the left, you didn't contract it, didn't touch it, well, it will stay there as uncontracted summation line. Okay, so the character cannot be changed. Well, unless, you know, you act on the feed, then of course you may have to do this sort of the turning the line procedure, right, to say extend them to the left. But that is something, you know, that is sort of a posteriori, very easy. It's very easy for you to just draw the line in one of the two directions. Okay. All right. So I guess we are now at a point where I think it's looking at some examples, just to sort of see how all these rules. I hope that we can see them. I don't know. I have to sort of stretch it across all these blackboards. I hope that this was readable. Was it readable for everybody? All right. Okay. So right now we'll try to simply practice. What I would like us to go into is, if you look at our content here, is what is called here section 4.2, where we talk about equivalent diagrams, skeletons, and weights. You know, it's really time for us now to learn how to remove these repetitions in Week's theorem when terms repeat themselves, okay, and how to read properly the corresponding factors, which we call the weight factors, okay. So in order to do this, we'll have to introduce the concept of a skeleton. So we'll talk now about multiple issues. Let's see. I guess I'll start cleaning this here. Have you copied all this? Okay, so maybe I'll erase. We'll now talk about, as I said, the equivalent diagrams, skeletons, and weights, right? So equivalent diagrams, here, actually, Fill on some weights. Okay, all right. And you know, we will focus here on cases which are most relevant in our examples, that is situations where we have expectation values of products of operators in the Fermi vacuum or products of operators acting on the Fermi vacuum. So let me start with example, I'm going to call it 1, where we will make an attempt to calculate diagrammatically the following matrix element: phi, Zn, phi, IA, okay, which formally is an expectation value of the product of two operators. Zn, that's the normal product form of our one-body operator, and EIA, which is an excitation operator. Okay, maybe as a reminder, EIA is a normal product of XA dagger XI. It's an operator that generates a singly excited slightly detector. Okay. We know the result. You know, the beauty of this is that we already know what has to come out of it. It has to be I little z a. Now the question is, can we get this result diagrammatically? All right, by drawing pictures. Okay, well, let's go ahead and do it. Load this up and start here. What I'll do now, I'll try to do sort of a diagrammatic as well as algebraic manipulations in parallel, so you'll see the steps that are involved. So what? First of all, you know our rules. Point 1: draw the diagrams from representing operators on the left-hand side. We have two operators here, Z and E. So Z, we already know what it is. Z is this picture, Zn, I should say, right? This is Zn, and we know that Zn is a summation over PQ, P little z, Q, normal product of XP dagger XQ. That's the picture for it. This line is P, this line is Q, and maybe I'll use a little bit of color, red and blue. Okay, we know that both lines are free. We sum them over. Okay, we also know that this vertex here, draw it nicely, little circle, filled circle, is simply a representation. It tells us that, you know, with this cross tells us that this is a matrix element PZQ. Okay, what is the other operator that we have? It's EIA. Okay, so that's an operator which we represent by a vertex. I'm going to use now that thicker circle, filled, because the small one I'm using here. There is a line A leaving, line I coming into it, and this is a diagrammatic representation of the excitation operator that you see right here. So I don't think I have to rewrite it. That's what it is. Okay. The difference between this and this operator is that those are fixed lines. So let's remember, they are fixed labels. Okay. What do we do on the right-hand side? Well, on the right-hand side, I'm supposed to, so I'm going to start doing what you would do in the right-hand side. You would just write sum over PQ, P little zq. You would have an expectation value, normal product of XP dagger XQ, a normal product of XA dagger XI, and cat phi. That's the left-hand side, and then you look at what are the possible contractions in it. And you remember this, because of the generalized mixed theorem, there's only one contraction. You have to contract Q with an A and P with an I. Okay? We know it already from our algebraic considerations. Okay? So that means that you end up with, so let me continue. You end up with sum over PQ, you have P little zq, you have phi, a normal product of XP dagger XQ, XA dagger XI, phi,
and the contractions will be Q with an A and P with an I. And then you read it, we did this, we know that we end up with IZA. So maybe I'll move this, and because you can help me again, if we could have those two blackboards seen for the next some minutes, because I'll be doing sort of working between the two. Okay, so we end up with IZA. That's algebra. Well, the algebra suggests that I have to connect line A with a Q and P with an I. But now the question is, would you figure this out without looking at the algebra? And the answer is yes. I'll go back a little bit, because I have to draw a little bit more. If you look at this picture, I know that I am computing an expectation value in the phi. Maybe as a reminder, normally we don't do this, but I'll wait so I use a color to emphasize that's not part of the diagram, but it's sort of a reminder. That's what you're doing with it. You're putting this between the phis. Well, if you do, then you have to contract all the lines. But you're not supposed to contract P with a Q because it's a normal ordering. Can't do that. So P has to go elsewhere. It doesn't have many places to go. Can only go into I. Okay? That's all it can do. So what you have to say is that I'm going to be contracting this with an I. And then I'm left with Q being forced to be connected with an A. Because we have to connect lines with the same orientation. You see, I didn't have to look here to figure this out. The diagram tells me what's the contraction scheme and what's the only contraction scheme. All right? Now, we don't draw diagrams in this chaotic way. In the final presentation, that's what you do on your scratch paper. Once you're done, you present them to the public nicely. So you stretch, you sort of strengthen. You sort of straighten. Straighten every line, okay, so that they are not so kind of, mixed up, right? So we're going to end up with, what is the picture that comes out? I have two vertices, okay, and you can see what happens. And please don't pay attention to the right-hand side, the algebra. I have to connect A with a Q. A is fixed. Q is free. Well, what did we prove before? When you connect fixed and free lines, the result is fixed, labeled with an index of a fixed line. So this A going into Q has to be labeled as A. So I start, and that's, I go this way, and I'm going to label it with an A. Well then, you can kind of really follow with, say, your pen or something. You can see, I'm leaving from here. Imagine like I'm a little tourist traveling on this, right? So I'm traveling, going on the A, going into Q. I know this is line Q. I'm here now. I have to go back. So I leave with a P, go back on the I. But P combined with I is I. P is free. I is fixed. So it's going to be I. So I know that the missing component here is this. And that's the resulting diagram. You can see there's only one. And the question now is, why is this diagram this? In other words, I know the result, so I got it here, right? But the question is, can I get this number without doing any algebra? Just looking at the diagram. Yes, the answer is yes. So now, let me talk about this. Remember, resulting diagrams have this familiar structure. Sine, and I hope that you will remember the symbols. Sine, weight, summation over internal and external indices, right? The scalar factor, labeled by both kinds of indices. I'm writing a generic expression. And the operator part, labeled by external lines. That's how any KR, any resulting operator should look like. Well, let's see. But we're doing an expectation value. If you're doing an expectation value, you will not have this part, because there are no external lines. Just cross them out, right? So in the case of an expectation value, your expression simplifies. It has to be a sine, a weight, a summation maybe over internal indices, which I call with chi prime, and the scalar. So somehow I have to believe that this is this. you know, you have to convince yourself somehow that this is right. Well, if that is right, we know what the internal lines are. We have only two internal lines, A and I. So we know that our chi, our prime, is really a set of two indices, I and A. Nothing to sum over, really, because they're fixed. If this is a right expression, let's now make a big if. We know it's a right expression, but if this is a big if this is a right expression, then the sign should be +1, because there's no minus. The weight should be 1 somehow, and the scalar factor, if all of this is a right formulation, should be IZA, right? You agree with me? Those are the requirements of this calculation, if we believe our representation and the way and the workings of it this way. Okay, so let's convince ourselves that indeed the sign is 1, the weight is 1, and the scalar factor has to be what I just wrote. Okay, let's do a little manipulation here on this blackboard. You'll begin to see some cool things. I'll use this topological representation, you know, to really, you know, kind of, since I'm using you already this topological language of the scalars and all these things, right? I want to, let's sort of use it more. So what is Zn in this topological representation we're using? It's the weight, there's no sign there, okay? It's the weight of the Z, okay, call it Zn. You're summing over indices of this, which are only external in the Z operator, so let's call it chi Z double prime. We have some scalar there, okay? Z, okay, Z is enough, chi Z double prime, and then there is an operator part. And actually, not to make it so mysterious, let's identify what these things are. In the Z, W, okay, is 1, the chi is PQ, right? This is what they are, and the operator part is a normal product of XP dagger XQ. So this is my topological version of the Z. What is the topological version of the excitation vertex? EIA. Once again, it's the weight of it. Let's call it weight of an EIA. There's a scalar. I'm going to just call it AI with an E here. Okay? If you miss the E, don't worry about it. Okay? And then we have an operator part of it, which is an operator part labeled with A and I. Okay? What are these three? Weight is 1. Scalar is 1. You know, there's nothing in the excitation operator. It's just the product of operators, right? So this one is 1. And what is the operator part? It's the normal product of XA dagger XI. Okay? So I just translated our algebra into sort of this topological interpretation. Okay? Well, what if I form a product? You know, what if someone tells me, you know what, use these formulas to process, you know, the expression using mixed theorem. Okay? So what's going to happen is this. Let me not leave the blackboard. And do the processing, okay? Okay, let's do some space here. So I want to know what is phi Zn EIA, but not using the second quantization, but using these topological forms. You can see I'm going to have a product of the weights of both operators. I'm going to have a summation over the external labels of the Z. Okay? I'm not summing over A and I because they're fixed. Okay? We'll have a scalar product of the Z, a scalar product of the EIA, this expression, right? I'm just copying. And then you will have an expectation value of the product of operators, defining these two operators. Okay, so one of them is called O chi Z double prime, the other one is O A I. Okay? You know, that would be a proper calculation. Let's start here. This is a bunch of creation and annihilation operators that you have to fully construct. Okay, here I'm not going to still do a lot of work. We know what happens here. You have to fully construct this. And here you know that the consequence of this full construction is that P, so I'll simply make a statement here that P becomes I and Q becomes A, right? As a result of contracting. We already know it from what is on the other blackboard. So P becomes A, P becomes I and Q becomes A. Okay? And then you have to propagate this information here. right? Summation will be gone, because, P, Q will be fixed. And you will end up with an expression which really has only three components. The product of the weights and the product of the scalar factors. Right? Where this is replaced by what is PQ? The IA. Okay? Well, I am supposed to get this one. This is an honest calculation. I haven't done actually any week's theory. I mean, of course, internal I did for the operator part, but I really, I'm trying to keep this topological form. If you compare the two, you can see what happens. In order for these things to reconcile all these things, you have to conclude that if I want to maintain this formula, I don't know how the sign becomes plus yet. I'll mention this in a moment. But the weight seems like it should be a product of weights. That must be WR, right? Because that's all there is to it. Well, what about the scalar factor that we wonder so much about in our formula, right? It has to be the product of the scalar factors. Okay? For the Z and for the E. For the E, you label it with AI, and for the Z, it is going to be P, it's PQ, right here. So P is I, Q is A. That comes from this construction. So in order for us to reconcile this form with that form, I have to calculate or interpret scalar factors and weights in this way. Well, look, weight of each diagram is 1. What's 1 times 1? That is 1. So you got 1. Looks like weight, in this case, is just product of weights. You'll see not always, but here is. Okay? You see, if I look at the scalar, it should be a product of scalars from each operators. But not with the original labeling. You see, that's the thing that Ron has already mentioned, right? Not with the original labels, because, the fixing of the indices propagates all over the place. Okay? So you have to read these scalars with the indices in the resulting diagram. Okay, so let's read it. I'm going here. I have to form a product of two scalars for this times this. Okay, so let's do this. Alright? Maybe I'll do it here. Okay, that's my favorite red color. I'm going to read that scalar. This factor is, remember how we read this. It's outgoing, Z, incoming. That's how we're reading these matrix elements. So it is I, Z, A. Right? Scalar factor for this, that's the DE, it's 1. We define it to be 1 to start with. So it's times 1. And you end up with, well, I have it here, right? IZA. You see, I got that information. I can just read it from a diagram. Just form a product of matrix elements with the indices of the diagram. Okay? You see, no need for algebra anymore. I can inspect my diagram and get the result. Alright? I got the right formula. I got the right weight. Okay, weight is tricky because weight is 1 here. The fact that product of weight gives you 1, that's kind of a coincidence because we don't have different diagrams. If we had equivalent diagrams, we'll see this next time. Then you would have to, pay attention to how weights are calculated. But right now, everything seems to be okay. Now, of course, you may ask the question, how do I know it's, okay, I know the sign is plus 1 because, okay, we do it from the start. But how would I know it without doing Week's theorem? Oh, well, we're going to prove a wonderful, wonderful statement that the sign is minus 1 to the number of loops in a diagram, we'll define what loop is, plus the number of internal whole lines. We'll prove it. It's a theorem. It's not my guess. Right? That theorem says that you have to look at your picture, count the loops. Well, I guess, I didn't formally define a loop, but I think you all agree that this is a loop, like a loop. So there's a loop, one loop. And H stands for the internal whole lines. How many internal whole lines do you see here? 1. So H is 1. Well, I guess the sign is plus. Minus 1 to 2 is 1. Okay, so you see, I don't need algebraic form anymore.
I can read all of this stuff, including every factor from the diagram, okay? Because I can tell you that when you learn weights properly, weight of this diagram is 1, because there are no transformations of the diagram that convert it into itself without breaking it into pieces, okay? And sine is 1, as I showed you from the rule we'll prove. And the scalar is nothing else than just form a product of scalars. And you're done. Okay? So this is the first illustration that the diagrammatic rules have a chance to work. So we'll have more examples, more complicated, next time. Okay? Alright. So thank you very much. See you on Friday with the hope that the weather will improve.